When we looked at queuing models expressed in continuous time Markov chains, we saw that the transition diagram was fairly simple. From state 2, you could go up by 1 to state 3 or down by 1 to state 1. And that was for an MM1 queue, but the same thing was true for like an MM3 queue with 3 servers. You could only ever go up by 1 or down by 1 at any particular transition in the models we set up. And that's a really common thing in continuous time Markov chains, and they're called birth-death continuous Markov chains because they only ever have one birth or one sort of death at a time. So that's the kind we're going to simulate. So we're coming to the simulate birth-death CTMC sheet here, and we're going to use the competing exponentials view of a CTMC. And we'll list the birth rate and the death rate for any particular state. So row 5 says which state we might be in. Row 6 directly under that says what's the birth rate when we're in that state. And row 7 says what's the death rate when we're in that state. We also have in A4 the number of servers, in B4 the arrival rate. You could say calls per hour. Right now I have it set to 21 and number of servers is 11. And in C4 the per server service rate, I have it set to 2, so 2 calls per server per hour. And then the actual simulation happens starting at the tables in row 9. So column A just tracks which event number we're looking at, event 0, event 1, event 2, event 3. We'll just start at time 0 in B10. In C10 we have the initial state. We can set this to start at state 0 if we want, or we can set it to start at state 9 or 100 or whatever we want, which is a little different than the simulation we were doing the other day, where the queue started out, the entire system pretty much had to start out empty. It was going to be very difficult to start it in a non-empty condition. And now, so that C10 is just a single number you type in for the initial state. Then in D10, that's where things start getting interesting. That's the birth rate in the current state, and that is a lookup into the table of what the birth rate is for any given state. Here I'm using the HLOOKUP function because the table is laid out in a horizontal way, where we usually lay things out in a vertical way and use VLOOKUP. But here I wanted to make it fairly clear that the state table with the birth and death rates is not organized at all the same way that the simulation table is oriented or is organized going event by event. So I could have laid it out horizontally or vertically, but I chose to lay it out horizontally here just to make that point that it's not at all linked to the way that the simulation table itself is laid out. And then we do the same thing for the death rate, again using an HLOOKUP into the table of birth and death rates. And then in columns F and G we have just simple uniform random numbers that we'll use to generate exponentials. For the time until the next birth, we just use the usual exponential simulation formula, negative log of the random uniform 0, 1, divide by the rate that we're given, so we're dividing by the birth rate. And then we do basically the same thing for the time until the next death, except if you're in state 0, you can't really have a death, and I have a 0 entered for the rate of deaths in state 0. But then we would be dividing by 0, and that causes an error in Excel. So I have a little bit of logic here saying if the death rate is above 0, then just do the usual thing, generate an exponential using minus log of a rand divided by the rate. Otherwise, give me a really high number, 10 to the 308th, that basically no other number in our reasonable simulation will ever be larger than. So it's basically infinity. And then in column J, we're saying how long until the next change. We have these two competing exponentials, one for the time until the next birth, one until the next death. So the minimum of those two is the soonest that a new event will happen. So that's how much the time will change. And then the state change in column J is just saying which one happened first, the next birth or the next death. If the next birth happens first, then our state change will be +1, and if it's not, then our state change will be -1 for the next death. So now think, how are we going to use this to update the simulation on the next row where we're computing what's going on with the next event? So the new time will just be the previous time plus the time change. The new state will just be the previous state plus the state change. And then after that, column D, column E, it's all basically just the same as it was in the previous row. And so then we just fill down from there. And imagine for a sec what the graph is going to look like. So we're starting in state 0. We're starting with an empty system. We have 21 calls per hour, an average of 2 calls per hour per agent, and we have 11 servers. Well, before we show the graph, maybe it would be fun to sonify the graph. So we'll highlight the state number column and sonify that. Here we go. So maybe you could hear a little bit of the warm-up there, starting really low and then warming up to higher numbers of people in the queue. We could try starting in a more kind of intermediate state. It'd be nice to start at whatever the long-run average is, but we don't know that usually, because that's why we're doing the simulation, to find that out. So I'm just going to sort of guess here that the average would be about 10. I actually know what it is, but we'll pretend that we didn't. And we'll run that again. Oh, so we didn't hear the warm-up as much there. Now we'll show the graph. Here we're starting in state 10, and you can see that the state got down to about state 2, and then climbed up above state 20. We can get new random numbers, and we can see how the state, the number of people in the system is kind of hovering around 10, but it can easily go up to 20, it can go down to 2. So that's the basics of simulating a birth-death CTMC. Now the graph we're doing here connects how many people are in the system at each time point, but it's each event time point, not each time point like on a regular grid. And the whole thing about CTMCs is the number of people in the system is defined at every time point, not just when events happen. So over here in columns P and Q, I'm doing something we don't usually need to do, but I'm just doing this for pedagogical reasons, to say if we do take a regular time grid of time points, and we'll use, so in column P I have a regular grid of time points, and in column Q, I'm using a VLOOKUP into the simulation table to say how many people were in the system at that time point. And then if we graph that, we can see that the number in system stays the same for a few time points and then jumps up a little bit and then jumps back down. So that's, in some sense, what the CTMC is really doing. It's staying perfectly steady until we have an event and then jumping up. Let's also try, let's try sonifying that. So here, we aren't going to hear very many changes, but the important part is some notes last longer than others. So listen for how long some notes last and how short some other notes are. All right. Let's do one more thing. Here we've been simulating an 11 server queue. I just wanted to point out that you don't have to have a nice multiple of 10 as your number of servers. What if we had an infinite server queue? Let's make a copy of this sheet and change it to be an 11 server, an infinite server queue, but also make it comparable to the other one. So I'm going to go to the number of servers here and put in some huge number, like 1,000. And to make it comparable to the other one, I'm going to make all the random numbers the same. So here in my new copy of the sheet, I'm going to say for the rand1 and rand2 columns, just equals, and then click on the other sheet and click on the rand1. So we're saying in the new sheet, F10 is equal to the old sheet, F10, and then copy and paste that all the way down for columns F and G. So now they're experiencing the same sequence of random events, but sometimes the rates are faster. I'm going to relabel state here as state_inf server so we can tell these apart. And if I look at the CTMC graph, it looks about the same. But what I can do is come over to the first one I had, hit copy, come to the second one, click on the graph and hit paste. And now I get two data series where the orange one is for the infinite server graph, infinite server simulation, and the blue one is for the finite server simulation, 11 servers in this case. Here you would you stop to think, do you expect the infinite server problem with the same arrival rate and service rate to have more or less people in the system on average than the finite server case? You would think, well, infinity sounds like you'll have more people around, right? But it's the same arrival and service rate. It's just that in the infinite server case, you can serve them faster if you have more people in the system. So we're seeing generating new random streams here. Most of the time, the infinite server system has fewer people in it than the finite server system because it never has anyone waiting in the line, waiting to get served and not actively getting served. So it's a nice little comparison between the two types. Next time we'll look at doing differential equations for the continuous time Markov chain.